Can one of you tell me? Yeah, stop. It's finding it difficult to. Yeah. Okay. Okay. I think last time we did. Right. Uh, we did further mechanics. Okay. We did start off with the energy momentum relationship. Right. Today we had to start off with elastic and inelastic collisions, right? So we are in further mechanics. Under further mechanics, um, last time we discussed about investigating collisions. Today it is on elastic and inelastic collisions, right? Elastic and inelastic collisions. Inelastic collisions. Right. Now, have you heard about this topic before about elastic and inelastic collisions? Yes. Is it at school or somewhere? Have you studied it before? Yes. Did you? No, right? It is completely new. Right. Elastic and inelastic means, right? For example, sometimes even in chemistry we apply this kind of theories. We assume when we are applying equations like PV equals nRT, the collisions are elastic. Right? Elastic means you can if I take a ball, a rubber ball here, and I am taking this rubber ball, and from the same height with the same mass, I am taking the plastic one. Right? If I released it from the same height, if I drop it, the rubber ball will what? Bounce back. It will not climb up to the exact height, but at least it will come near the initial height, not the exact height, a bit less than that. Why? Because certain energies, what? Getting wasted. If you release a plastic ball, what will happen? It will drop. It will not bounce back to the same height, but not even closer. Right? So if I talk you about a rubber ball, why it is climbing up more compared to plastic ball? Why it climbs up more? Yes. What is the reason? Can someone of you tell me? Why it climbs up more? Yeah. Energy wise, if you are telling the answer, uh, it is not 100% conserved, but most of the energy is not wasted, really, it is conserved. The energy here, it is energy transfer from potential energy to kinetic energy, right? But again it is bouncing back. Bouncing back means when it is bouncing, we can assume same kinetic energy is preserved, right? But here in practically, as I show you here, it is not climbing up the same height, rubber ball. But when it comes to plastic ball, right, most of the energies are getting wasted into, most of the time it is wasted into sound. And even though we can't see from your naked eye, bit of energy, the heat energy is also released, right? Sound energy and heat energy. Here, amount of heat energy being lost is very less, and amount of sound energy. When you drop a rubber ball, you don't hear much of the voice, right? Much of a noise, right? When you are dropping a rubber ball. But when you are releasing a plastic ball, you can hear the sound. So it means most of that energy is getting what? Released as sound energies, right? So remember, we assume now in physics when we are applying these equations, right? We assume when you when two collisions are happening, for example, now this is also collision. We assume this is just an assumption, right? When you drop a ball on the floor, it is climbing back to the same height. So as you said before, the energy is preserved. Potential energy into kinetic energy again back to the potential energy. So energy is preserved. So therefore rubber means rubber, right? Rubber is like an elastic. So these kind of collisions are called elastic collisions, right? Elastic collision. Why it is called elastic collisions? If you pull a rubber band, an elastic, from the two corners away from each other, and you can release it, it is coming back to the same position. Elastic, right? Same energies. When you pull an elastic, it is going to get stretched, and it is going to store some potential energy in the elastic as tension. Right? With the tension, it is storing some energy. And once you release it, the tension is released, it is moving back with a speed, and it contains certain kinetic energy, right? Elastic. Same thing is there, just like an elastic in a rubber ball, that energy is preserved. So in physics, when we are doing many of the calculation, we assume the collisions are elastic, right? Now, if you can remember, uh, right? Now remember this lesson. In this lesson, we are talking about collisions. We are assuming the collisions are elastic, right? But remember, in reality, when two objects are colliding with each other, these collisions are not elastic. So there are certain amount of energy being released as sound energy, sometimes even light energy, uh, and some proportion of the energy as heat energy. Right? Remember, that is the difference between elastic and inelastic collisions. Right? Okay. Is it understood? Right. Okay. Right. Now remember, right? I will give an example for an elastic collision. Right? In elastic collisions, kinetic energy is conserved. Right? Kinetic energy conserved. Right? In inelastic collisions, kinetic energy not conserved. Okay. Right. But remember, I told you certain proportions of energy is getting wasted. Energy is conserved. But remember, in both elastic and inelastic collisions, remember in both elastic and inelastic collisions, right? Elastic and inelastic, irrespective of the nature of the collisions, the momentum is always conserved. The total momentum is not going to get changed. The momentum conserved. Momentum conserved. Okay. Right. Now let's look at an example for elastic collision. In elastic collisions, remember, right? In elastic collisions, let's say there are two objects, they are colliding with each other, they bounce back, they move away from each other, right? Usually, in elastic collisions, when two objects are colliding with each other, they do not stick onto each other. Instead, what happens? They strike each other and move away from opposite direction. Move away from opposite direction. Okay, in elastic collisions. In inelastic collisions, what happens? When two objects are colliding with each other, they collide and they stick onto each other and they are moving at as one unit, right? So that is the nature of these two type of collisions. They stick onto each other and they move together, right? Move together, right? In elastic collisions, they move away from each other. In inelastic collisions, they stick onto each other and move together. Is it clear? Hello. Yes. Right. Now remember, when you talk about a mini explosion, for example, let's say inside the barrel of a gun. Let's say this is a gun. So inside the barrel of this gun, let's say there's a cavity. Through this barrel cavity, the bullets are shooted out. Right? Now here, let's say there's a bullet. This is the shape of a bullet. There's a screw actually, right? It is rotating around. Right? Theory of conservation of angular momentum, right? So now remember, these bullets are like a capsule, right? At this at this end of the bullet, there is a small pack of explosives. So when you fire it, what happens? There is a mini explosion happening at the back of this bullet, right? When we trigger the gun, so because of this trigger, there's explosion happening at this end of the bullet. As a result, there's a small explosion. This explosion is putting a force in both direction on the bullet and on the gun, right? Now, in this explosion, what can you tell? This explosion, is it a elastic collision or a inelastic collision? If we take this explosion happening inside the barrel of a gun, is can you consider it as a elastic collision or as an inelastic collision? What do you say? What do you think? Yes, elastic. Remember, I told you an explosion. Remember, it is not elastic. Remember, most of these energies are released when you are firing a gun. What do you see? You can see light, right? Sparks are released. Sound energy is getting released, wasted. Sound energy. Most of the energy is sound energy, and light energy also. Light energy. Uh, So, will the kinetic energy is conserved? What do you think? Will kinetic energy conserved? No, right? Kinetic energy is getting wasted into sound and light energies. So this is not a elastic, this is an inelastic collision, right? Remember, inelastic. Right? But still, the momentum is conserved, right? Momentum means if we take the gun, we call the gun recoil. So because of the force from the explosion on the gun is what? Moves back like a shock. So therefore, only a trained person can trigger a gun. Otherwise, if this explosion is strong enough to even to dislocate a shoulder or dislocate the what do you say a wrist of a person. If you do not hold it tightly with the right position and the technique, that shock, the power is strong enough even to dislocate your wrist or your shoulder. If it is a big gun, even your shoulder or maybe your elbow. So that is why only a trained person can handle a firearm. There's a huge recoil on that, right? Okay. So now the gun is moving back, moves back, right? Okay. It moves back, right? Because of the recoil. And the bullet is also getting the same amount of force. Bullet is moving forward through the screws, right? Now, between this gun and the bullet, which object is having the greater mass? The greater mass is the gun, right? I told you, even though whether it is the collision is elastic or inelastic collision, still the total momentum is conserved, right? Total momentum means at the beginning, total momentum is zero. You know, momentum is also having a direction, right? Momentum means mass. If the mass of the bullet, I am calling it as m1. From left to right, I am calling it positive. The direction is m1 into. If the bullet is moving at u velocity, mu, and the gun must move in the opposite direction. Therefore, I am calling it minus. From right to left, it is moving at what? V velocity, and the let's say the mass of the gun is m2 into v. Huh? So let's see how fast the bullet is moving. So therefore, you can make U the subject. U is equal to M2V divided by M1, right? Now remember, the gun is recoiling at a very higher velocity, and the mass of the gun is also very high compared to the mass of the bullet. Usually, you know that, right? Bullets are lighter in mass compared to the mass of the gun. So when you take the ratio between these two, right, M2 is a greater value. So anyway, the ratio is a very higher positive value, right? So therefore, that is why bullets are moving at a very greater speed, right? Okay, now with this equation, you can find the bullet of the velocity of the bullet, right? Now, why can we use this? Initially, the total momentum is zero before the collision. So after collision also, momentum must be zero. So therefore, if the gun is recoiling at this momentum m2 multiplied by v, the momentum of the bullet must also be the same. M1 multiplied by u is the momentum of the bullet, and this is the momentum of the gun. So they must cancel off each other because we discussed whether the irrespective of the collision, whether it is elastic or not, still the total momentum is preserved. Total momentum before is zero, total momentum after is again should be zero. So therefore we are plugging the values and we can find the momentum of the bullet if we know the two masses and the velocity of the gun recoil. Or you can find any value with the other values or not. Right? Is it clear? Uh, and also same can be applied into nuclear physics. You know, uh, nuclear fission means we have unstable nucleus. It has protons and neutrons, very unstable. They are repulsing with each other like uranium and thorium. We are shooting it with what? Another neutron. Then what happens? This is getting splitted, and these are splitted into smaller particles. A mini explosion. This collision, is it elastic or unelastic? This is broken into little masses and they are going to break away into different directions with different velocities. Is this mini explosion an elastic explosion or non-elastic explosion? What do you think? Non-elastic. Again, energy is getting wasted. All these particles are not having the same kinetic energy. Total kinetic energy is going to be different, right? Initial kinetic energy of the neutron and the after collision kinetic energies of these little particles are not going to be the same, right? Some energies are getting wasted and they are radiating outwards. Radiating outwards, radiation as radiation are gamma particles, alpha, beta, gamma, very high energies, right? So that is why nuclear explosions are very dangerous, right? But anyway, we can still do this explosion, we can still apply the conservation of momentum theory, right? We still plug in the values and find, right? Okay. Uh, You know, if I give you a reminder on kinetic energy, the equation for kinetic energy is what? Ke equals half mv squared, right? Just a reminder. Mass multiplied by velocity, right? Kinetic energies are not getting preserved in the inelastic collisions, right? But whether the collision is elastic or non-elastic, the total momentum is going to be preserved. Remember, momentum is also a vector quantity, right? So that is why we can cancel off, or we can add, or we can subtract the velocity in vertical and horizontal directions, right? Okay. Uh, I will give you a question, and let's say you can do it. Is it clear? Everything we have discussed so far, right? This is the question. Let's say there's an object with a mass of 0.80 kilograms. Let's say a little train, and there's another stationary trolley on the same leveled road. You have this a stationary trolley, right? Stationary, right? And this trolley, the moving trolley is moving at the direction of the stationary trolley at the velocity of 3 meters per second. And the masses, when we compare, if the mass of this trolley is m, the mass of this trolley is 2m, right? And after collision, the trolleys are now sticking together and they are moving as a one unit at a velocity of 1.0 meters per second, right? Now the question is, you must determine, you must show whether this collision is an elastic or an unelastic collision. Elastic or non-elastic collision. With the equation, you must show whether this collision is a elastic or non-elastic collision. Can you do it with the correct steps? Okay. Usually you are not, okay. You are not given the diagrams also, but I have given you the diagrams. Let's see. Send me your answers for me to check. You can do the question in two steps. So the point here is we should show the initial kinetic energy and after collision kinetic energies, and show there are the difference in the kinetic energies, right? And also we can show whether the before collision and after collision their momentums are different or same, right? So we don't need to show it, but let's see before collision and after collision whether it's same. So before collision it is what, 0.80 into 3. After collision I told the mass is twice the mass, there should be 1.6 into 1. Yeah. Ah. So twice the mass. So therefore it must be 3 times. So 2.4 into 1. Yeah. So both the values are the same. Before and after it's the same. Here it is also 2.4. After also it is 2.4. It should be like that. You don't need to prove that. Right? So it's just a matter of finding the initial and after kinetic energy difference. Right? So it must be initially the total kinetic energy must be greater than the after kinetic energy. So let's see whether there is a difference. Delta E, delta E kinetic, initial half mass zero point 0.8, V squared means 3 into 3, subtract half mass is what? 3 of these, 2.4, right? Into 1 into 1. So let's take this one out, common factor out, 2.4, 8.8 multiplied by 3 means 8.4. Within brackets, 3 minus 1, right? Yeah, there's a difference, right? I took the common factor out. So 1.2 multiplied by 3 minus 1 is 2, right? Uh, 2.4 joules difference. Yeah, very small. Uh, yeah, because the masses are very small. So only and the velocities are very smaller. So therefore only very little amount of energy is getting released over the 2.4 joules of kinetic energy is getting wasted, right? So as per my calculations, uh, oh my bad, did I do anything wrong? I did the calculation manually. 2 3 into 2, okay, half, yeah, yeah. So I'm getting a 2.4 energy difference. Yeah, that's correct, right? So that's the value. Let's see with the 100%. Yes, right. Or you can do the calculation separately and find whether and show initial energy is greater than the after energies. Right? Okay. Uh, right. Now let's move on to energy momentum relation. Put the heading as energy momentum relation. Okay. Deriving energy momentum relation. So we are going to derive it. Subtopic deriving the energy momentum relation. Give me a second. Okay. Right. Now under this deriving the energy momentum relation. Deriving the energy momentum relation. Energy momentum relation. Now the equation for calculating the kinetic energy of a particle moving at velocity v ek, sorry, you know the simple equation, half mv squared. Right? If a particle of mass is having a velocity of v. For the same particle, the momentum is what? It should be mv, right? Same symbol. This is the momentum. Right. I'm going to give you a task. Right? Can you derive the equation for EK, kinetic energy, using in your final equation you can only have P, velocity, and only mass, right? So we are going to derive the equation for a relationship between kinetic energy of a particle and the momentum of a particle using the mass of a particle, right? So in your final equation you can have only P and M. Derive an equation for EK. Can you all do? We'll see. You need only basic oral mathematics. Can you do it? Can you? It is not that hard. Yeah, very easy, right? Even a middle school child would do. Ah, don't be in a hurry, right? P square divided by 2m. So what we can do is in the first one you can make V the subject. So there are many ways of doing it. This is my way of doing it. I am going to make V the subject here and P divided by M here. And I am going to call it as what? This is the first equation, second equation, third one. Then I am going to using first and second, first and third. I am plugging the values. EK equals half M. Instead of V squared, I am plugging the value of P over M squared. What do you get? Half M P squared M squared. M to M getting cancelled off. So you are getting it as what? So half P squared. Right? You should know how to derive. Very easy equation, right? So you can check whether is your equation is correct by looking at its units, right? You must have the same units, right? So once you plug in the units for uh, momentum, momentum is what? Uh, Kilograms, meters per second, squared. Units for m is m, right? Same unit must be there. So um, this kilograms, right? Sorry, right? So you are getting only what? Kilogram. There's only 1 kilogram there. Meters per square second, right? Kinetic energy of half m is squared. Half m means half m means kilograms. V means velocity. Velocity means m s squared. Kg m squared per second squared. Same units, right? They from that you know whether your derivation is correct or not. Right? You must get same units in the both sides of the aisle, right? Okay. Uh, But I'll give a question straight away, right? Uh, Calculate the kinetic energy in mega electron volts, right? Mega electron volts of a particle which has a momentum of, this particle has a momentum of 1.1 into 10 to the power of minus 19 kilograms meters per second. Mass of a proton, now we are talking about alpha particle. It's an alpha particle. Mass of a proton is given as 1.67 into 10 to the power of minus 27 kilograms. Mass of a neutron is given as 1.67 into 10 to the power of 27 kilograms. More or less the same, right? Calculate the kinetic energy in mega electron volts. Fine. Fine. First find the amount of energy, right? Then convert that into mega electron volts. How to convert mega kilo? What is the relationship between joules and the mega electron volts? I have an answer. Okay. The unit conversion is the thing, right? Okay, we'll come on to that later. Um, First of all, you can either derive the equation and find, or you can plug in the derived equation, right? I would prefer deriving it and finding it. So what I would do here is P is given. I need to find the energy, right? So I will take the energy equation first. Half mv squared, right? Then what I would do is I would multiply this and square it and divide with m, right? So I know when I do it, uh, yeah, half m squared. Yeah, I would square m, right? I would square m and leave v squared as it is, and I will divide it by m, right? Still the same thing, no, m to m getting cancelled off. Half m squared, the equation is there. So still it is what? M into v squared means p squared divided by m. Same thing, right? So I just divide it right now in one step. Then what I would do is I'm going to find EK value, right? Now before plugging the EK values, I need to do the unit conversion. They're asking about mega electron volts. Mega means what? A kilo means kilo, mega, giga, tera, peta, right? 10 to the power of 3. Kilo means 10 to the power of 3. Mega means 3 into 3, 10 to the power of 6. That is mega. Electron volt means, by definition, the amount of energy stored in electric field if you have a particle, when a charged particle is in an electric field, the amount of energy stored in this particle. That is the definition of voltage, right? So one voltage means, right? That is the definition of electro. Voltage means joules per coulomb, right? That is the definition of voltage. Amount of energy stored in a 1 coulomb particle in an electric field. Amount of energy stored in a 1 coulomb particle in an electric field, right? So amount of energy is joule per coulomb. That is the definition of